Hi everyone, my name is Jose, and today I'm going to talk about our current firmware update design. So this has been a joint work between ARM and the Ledge team from Linaro, and I also wanted to point out that we're going to talk about firmware update, but it's entirely focused on A-class devices. So there's a lot going on when we're talking about firmware delivery, and we start off by someone having to write the firmware. This is the job of many different teams. Then the firmware images are signed and bundled together in a package. The package gets uploaded into some server or to some cloud service and eventually sees its way onto your device. Then at this point, it's the job of the OS within your device to find a way to deliver and install the different images that it receives from the package. And this is really what today's presentation is going to focus on. Really this last mile of the firmware delivery. And it's also what we're focusing on our firmware updates projects. So I'd like to start off with just some minor clarification in the terminology. We all know that UEFI is an industry standard, that it defines an API and a group of data structures, and that there are many UEFI implementations. So it's not just EDK2 as sometimes we tend to assume. U-Boot is also an example of a UEFI implementation. So during this presentation, whenever I mention the term UEFI implementation, I'm actually referring to both U-Boot or to EDK2. So let's start off with the technical aspects. I'd like to point out initially that we're supporting a diverse, or at least recognizing a diverse set of platform designs with respect to which entity owns the flash where the images are stored. So we see these two distinct platform designs, number one and number two. In platform number one, the normal world controls the flash. This requires more resets because we need to ensure that the normal firmware is executing in isolation and has sole ownership of the flash when it's writing the images, when it's updating the firmware images. But we will never fully isolate the firmware storage from the OS. So a malicious or compromised OS will always be able to access the firmware storage and either thrash the images or try to override some of the images with some compromised images. And a counterpart to this is platform number two. So in platform number two, we're seeing this as an emerging trend, is by no means the default. But we're seeing this picking up as a design in the ecosystem. So what this design has in particular is the flash where the firmware images are stored in is owned by the secure world. So in this case, the normal world OS receives the firmware package, it unpacks the images and needs to transfer those over to the secure world. And then the entity in the secure world, which we term the update agent, is responsible for writing the different images in flash at their correct offset. So this platform model with respect to the firmware update just requires a single reset for us to do the entire update. While the images are being transferred to the secure world and written to flash, the OS can continue on executing on the other cores. So we're minimizing system downtime. And because we're isolating the flash where the images are stored from the normal world OS, we're mitigating against a set of attacks which we wouldn't be able to with platform number one. So platform number two is both more secure and minimizes system downtime, and it's really the focus of our work. So our work is really to enable platform number two and for us to enable firmware updates on platform number two designs. Some of you must be thinking by now that there already exists a firmware update standard, and that's true. It's the UEFI UpdateCapsule. We're not really doing anything different from UpdateCapsule. We're really, in a nutshell, just building on top of what UEFI UpdateCapsule already defines. So that's mostly because it's a well-understood model, widely tested. The OS is already interfaced with it, and there's quite a lot of body of code that knows how to interact with it. So we're not reinventing the wheel here. We are just going to add the missing bits to enable the platform number 2 design from the previous slide. So the update capsule abstraction is going to govern the interaction between the OS and the normal world firmware. But in the platform number 2, we are going to require some glue that bridges the gap between the normal world firmware and the update agent over in the secure world. So that's the first thing that we're standardizing. It's this firmware update ABI that's used by the normal world firmware to communicate the images over to the secure world. The second bit that we're standardizing is the usage of the AB model. So the different firmware images in your system are going to have more than one instance. And the different instances of these images are going to be grouped together into the entities that are generally called as banks. So you're going to have, for instance, the bank A and the bank B. If we are to provide a layout for your firmware storage based on a GPT, the GPT doesn't really have out-of-the-box support for A and B partitions or A and B banks. We are introducing a data structure that extends the GPT slightly, and that allows us to create this abstraction of the A and the B banks. So that's the second bit that we're introducing in our standardization efforts. So let's take a step back and look at the different agents that are present in the system implementing the firmware update procedure. We have the OS, the normal world firmware, listed here as U-boot and EDK2, the update agent, which is the entity that writes the firmware images to flash, and the platform boot code. So the OS and the normal world firmware are going to communicate using the UEFI UpdateCapsule interface. The OS passes on the capsule to the normal world firmware, and the normal world firmware will in turn create the ESRT table so that the OS is able to discover the different firmware images in the system and their versions. So the normal world firmware is going to communicate with the update agent by sending the firmware images using the firmware ABI that we're standardizing. And this firmware update ABI builds on top of a shared buffer and a synchronous event. The update agent will in turn send over the state of the different firmware images in the system to the normal world firmware. And because we said that we want to support the AB model for robustness sake. And so when the update agent is writing the different firmware images in Flash, it doesn't always write them at the same offset. If we're updating bank A, the images are going to be written in the offsets of the images in bank A. But if we're updating the images in bank B, the offsets at which we write the images are going to be entirely different. The platform boot code needs to understand whether we're booting from bank A or bank B in order to discover what are the offsets that it needs to fetch the different images from. So we said that the GPT does not easily provide out-of-the-box support for A and B banks. And we also said that we decided to introduce a data structure that creates this bank abstraction. That's the firmware update metadata. So this data structure is written by the update agent in Flash as a partition in the GPT, and the platform boot code is going to inspect the information in the firmware update metadata during boot time to discover which of the banks it needs to boot the platform with. Now, let's leave the robustness aspects aside and let's focus on how does the Flash actually look like. To the update agent, it looks like regular Flash. You are going to have many different images at different offsets. The update agent is always going to be able to access the entire Flash. It's going to see the different image types that belong to different banks. In this slide, we see here, for instance, one bank showed that with the images in light green, the other bank B, has the images in light gray. So the update agent is going to see all of this, but it exposes to the normal world a different view. So the normal world isn't really going to see the entire flash. What it sees is a set of files. And each file is going to be named by the firmware image type UUID. So for instance, the EDK2 images will have a specific UUID, and the TFA image are going to have a different UUID. And this UUID or the file name is going to be the same whether we're looking at bank A or bank B. At any point in time, the update agent exposes via the firmware update API this file abstraction, and the files that the normal world is able to see via this interface are the files that are in the bank that's being updated. So the other banks in the system are not observable from the normal world's viewpoint. So all of the files here are going to have a specific representation in Flash, apart from this very particular file that we represent here in orange, which is the firmware directory. The firmware directory is not necessarily the information that's used to construct the firmware directory does not directly come from Flash. It's kind of a fake file created by the update agent that transmits the information about the different images that are present in Flash and their UUIDs, and the permissions with which the normal world can access the different files in Flash. The primitives on the firmware update API are listed in the column on the left. And on the right, we have the state machine that we use to model the system. We have three states: the regular, staging, and trial. Your platform is going to be operating mostly out of the regular state. We will only go to the staging and the trial state whenever we perform firmware updates. So once we receive a package of firmware images to install, your platform needs to call firmware update begin staging to transition to the staging state, and only when in the staging state will the normal firmware be able to write new images into Flash. So after, when we are in the staging state, then we need to open the different files by invoking the firmware update open call, after which the normal firmware needs to invoke firmware update write stream consecutively to transfer the full image. And once the image is transferred to the secure world, then we need to call firmware update close. After all the images are transferred, the normal firmware terminates the staging state by calling firmware update end staging. And once we call this function, the system is going to transition to the trial state. And the trial state is characterized by all of the images that we've just installed being in an unaccepted state. And the trial state will only end when all of the images have been accepted. To accept images, the normal firmware can invoke firmware update accept image and passing the UUID of the image that it wants to accept. So once all the images have been accepted, we are going to transition to the regular state. And a further aspect of this is if we want to increment the value of the anti-rollback counters, we will not do so during the trial state. And the reason for this is we don't want to rush incrementing the value of the anti-rollback counters, because this would prevent us from having a fallback path to a previously working bank. So we will wait until we verify that all the images are working correctly before we increment the anti-rollback counters. And we only really verify that all images are working correctly once we transition to the new regular state. So if anything goes wrong in the trial state, if the new images fail to boot the system, we will always have a fallback path to the previously working bank, in this case, bank A. Likewise, if something went wrong during the staging state, as we were transferring the images over to the secure world, we will always have a fallback path to the bank from which we're currently running the platform from. So now I just wanted to quickly go through the end-to-end firmware update flow, starting from the OS, because this is an OS-triggered firmware update, and we will just quickly see all the steps that are involved. So initially, the OS reads the ESRT table from the firmware, and it discovers the different images in the system and their versions. And then the OS identifies whether it has a firmware package that can be used to update the images in the device. And if it has one, then it passes it over to the UpdateCapsule runtime service. Then when the normal firmware receives the UpdateCapsule call, it's going to transfer the different images over to the secure world using the firmware update API. And as we transfer the different images over to the secure world, the update agent goes and writes them into Flash. And when this process completes, we're back in the normal firmware, at which point we can either trigger a system reset, or we can return to the OS, and the OS then needs to explicitly call a system reset. So at this point in time, the new images have been installed and written to Flash, and we're prepared to boot the system using the newly installed images. So the system is going to start booting with the newly installed images, and as we manage to boot the platform up until the normal firmware, we need to signal to the update agent that all of the images seem to be working correctly, and then the update agent is going to mark all of the images in the metadata, because it's in the metadata that we track the acceptance state of the different images. And as we return to the normal firmware, then we will boot the OS. And again, the OS, during its bootloader phase, it's going to inspect the SRT table and verify that the firmware images were correctly updated and are now at their new version. So the standardization effort that I've been talking about during this presentation is really embodied in this spec, which we've currently published at an alpha quality. So it's not yet the final release. We're still iterating on it, but it describes the ABI and the metadata, and it has some other guidelines around it. But it's mostly covering the interaction between the normal firmware and the update agent over in the secure world. For the end-to-end flow, we're working on an end-to-end design document that focuses on UEFI and how the UpdateCapsule implementation uses the tools provided in this specification. But this UEFI end-to-end document, it's still under development. It's not yet published. But using what we've been describing here, and mostly I've been standardizing in this first document, we've created a prototype on the QEMU platform. There we've written the update agents, or a prototype version of the update agent in the standalone MM, which runs on top of Opti. And for the normal world firmware, we've used U-Boot. So the U-Boot implements the update capsule that communicates with the update agent over in the standalone MM. And of course, for the boot code, we've used TFA's BL2. So some aspects of this prototype, we've started upstreaming them to U-Boot. So we're taking the steps to productize the prototype itself. But yeah, this is yet very much just an investigation at this stage. So here I'm listing both a link to the current prototype and also to the alpha release of the specification. And I'd really just like to finalize the presentation with this plea, or I really wanted to stress that the specification is only released at alpha. So this is not the final release. We're taking feedback, and it's really important that we recognize that this is a community effort. So what we're standardizing here is going to benefit all of us. And it's important that we take the input from everyone that's interested in this functionality. So I invite you to go and look at the current specification and provide us with comments or your own view on which functionality is lacking, whether we're overly specifying the functionality. It would be really great to hear from you. So here's my email. If you have any comments or suggestions, please do send me an email.